In addition to the geometric series, we'll encounter other types of series known as the harmonic series. So this series is called the harmonic p series, where the terms are the reciprocals of n to the power of p. And for the special case, when p equals 1, then we have the harmonic series. And this is represented graphically over here. So if we expand a few terms, then we can see that the harmonic series gives the area enclosed by these rectangles. And another type of series we'll encounter is the alternating harmonic series. So in this case you'll have powers of -1 multiplied by 1 on n. So this will give 1 minus a half plus a third and so on. And you can generally see that the harmonic p series is positive and decreasing, so we can define a function from it that's positive, continuous and decreasing, and thereby use the integral test to derive the convergence conditions. Let's derive the convergence conditions for a harmonic p series. So we can define a function that's positive, continuous and decreasing from 1 to infinity, and integrate this with respect to x. And given that this is an improper integral, we can take the limit of a dummy variable. So if we evaluate this integral, we'd obtain the following limit. Or we can write this in an eta form of 1 minus p. And therefore, the limit is written as follows. If we take 1 on 1 minus p outside the limit, now for the special case where p is less than 1, then you'll have b to a positive power, and as b approaches infinity, so does the integral. So the integral diverges. And if p is equal to 1, then you have a divide by 0, and the integral also diverges. And if p is greater than 1, then what you'll get is reciprocals of b. So for example, 1 on b, 1 on b squared, and so on. And as b approaches infinity, the integral therefore converges. So therefore the series diverges when the exponent is less than or equal to 1, and it converges if the exponent p is greater than 1 by the integral test. Let's determine if the harmonic series converges using the integral test. So we can see geometrically that the series gives the approximation to the area under the curve 1 on x using the left Riemann sum with a rectangle width of 1. So the function is positive, continuous and decreasing from 1 to infinity, so we can use the integral test, which gives the area under the actual curve 1 on x. And if this integral diverges, then so does the series, because that gives a larger area than that under the curve. So we can evaluate this improper integral using dummy variables. And this gives the following result. And as we can see, the natural log of 1 is 0. And as b goes to infinity, so does the natural log of b. So therefore the series diverges. So even though these terms keep getting smaller and smaller, the rate of convergence is very slow. So the sequence of partial sums will never converge. Let's determine if the following series converges using the integral test. So we can see that the function is positive, decreasing, and continuous on the interval from 1 to infinity. So we're going to get a positive area under the curve, and we can apply the integral test. So therefore we integrate the equivalent real function from 1 to infinity, and because it's an improper integral, we can introduce dummy variables. And that gives the following result. And then evaluating the integral at those limits of integration, we can see that as b goes to infinity, this term goes to 0, and the limit evaluates to 1. So the series converges.